In this video, I will attempt to provide evidence that electric currents are responsible for some of the surface formations that we see on some of the planets and moons in our solar system, more specifically Earth and Mars. There are two main types of electric current that we'll be studying in this video, one being atmospheric electricity, which is electric current that travels from the atmosphere to the ground. The other being telluric currents, which is electricity that travels through the Earth's crust and seawater. The primary source of energy we'll be using in this video is a neon sign transformer, which is rated at 12,000 volts. And in the first experiment, we will apply this voltage to a piece of wood. In this case, it's a pine board. Here we have the board set up, and we have to use a little bit of solution of mixed salt water, roughly about 25 to 1, depending on the type of salt that you use. This is Dead Sea salt and tap water. And we'll see what happens. As you can see, the filaments race out in different directions, finding the path of least resistance until they connect. And once that connection is made, you will continue to see the carbonization of one path across the board, which the current found to be the least resistant path. If we turn the current off, you immediately notice that. But we can also observe the formation of what we're looking for in grand detail. Okay, in this segment we'll be taking a look at the atmospheric side of the equation. There are two main types of atmospheric discharge. One, everybody I'm sure is aware of, is the arc discharge, which is lightning. And there's another type of atmospheric discharge called electrostatic discharge. This has been recently posted in our news as, you can look it up as dark lightning. However, it all depends on the amount of energy and the duration of the event as to what will form on a surface. Here we have a little setup. I got a little actuator table set up to move the base plate back and forth. This is just an iron plate set on top of a neoprene block. And in order to get a electrostatic charge and not an arc discharge, you need some sort of dielectric material or a dielectric barrier. Look that up. This is just an insulated material such as this plastic, or in this case we'll be using sand in most of these experiments, and sand is dielectric. However, electricity will still flow through it. It's just at a very restricted rate. Its resistance is very high. So the first test we'll do is take, again, we'll have a piece of plastic on top of this iron. The iron's grounded, and then the electrode to spoon is the other lead. We'll place a small amount of sand in the center. Adjust the electrode and where it almost touches. And we'll just turn the power on wide open, and you'll watch what it tries to do. This is what we'll be monitoring at a much closer angle. But as you can see, you get a separation, which is indicative of electric discharge, that where you have material being ejected in two directions and nothing is literally being ejected in the opposite perpendicular directions. The next test we'll look at, we'll remove the glass, plastic, and we'll go ahead and add a whole table full of sand here. And this creates a dielectric barrier which will not allow an arc to form. We only use the electrostatic discharge. Let's smooth that out with a little trowel against a smooth surface. And this back. Set that spoon down. I'm going to show you a few of these from above, and then we'll move that camera down at a much steeper angle, straighter angle to see these. We turn it on, let it set for a few minutes. We'll be able to observe what this creates. And again, we'll look at these in slow motion and much closer with high resolution. Let's turn that off. And if you can see that, we'll turn the light over on it. See if you can catch that bullseye crater there. It was formed in the center of the sand. It's more of a crater in a crater in a crater formations. Okay, so let's move the camera down and get some closer looks at these with different electrodes. And now we have this camera zoomed in extremely close. I'll be able to adjust the current flow here as we move. As soon as I turn this on, we'll notice in the center, when everything clears up, we have these pillars, particles that are magnetically attracted to the spoon, and they're lined up in, almost, well, we'll see the almost perfect cubical columns, granule columns appear. And we can almost stop this in its tracks. If we turn the current down, we'll see that the attraction still remains fairly strong, and these they'll start to fall apart as I turn it down lower and lower. And when we get the current turned all the way off, the entire discharge is finished, and we'll see formation that occurs under the discharge area. So it turned loose then. And so if we move the spoon, you see what we have left. Now let's do this on a little bit larger or wider angle or a wider discharge area. And let's set that up. Okay, in this test we have a copper plate. It's a little wider discharge area mounted over the dielectric medium, the sand. We'll go ahead and turn on the current. And we'll immediately see many particles attracted to the plate, and they dance around in columns. They'll almost appear as granular columns, stacked grains of sand. And if we slowly decrease the current, catch them dancing around, try to zoom in, as close as we're going to get. And then if we turn the current off, and everything kind of sits in place, and you can imagine if they were scaled up, we'd have incredible amounts of heat that would almost form these long, tall structure. And then, of course, afterwards, what we end up with is, an entire area of peaks, valleys. And in my mind, this could very well be responsible for a lot of the formation seen on planets and moons. In this segment, we'll be using high-speed footage, which I've uploaded and we do on screen capture because it doesn't record audio. And here we have an iron electrode, a single iron electrode over the same iron plate we've been using before. It's a little different medium. This medium is a mixture of flour and aluminum at about 100 to 1. The source of power we'll be using for this experiment is a 19 million volt handheld taser, which produces a substantial spark or bolt of energy, which we will see when I turn the video on, that creates an digging process that certainly could be responsible for a lot of the craters that we think are impact craters, and this could have some implications with volcanic activity as well. As we've seen in previous videos, you don't necessarily have to have the plasma light in order to evacuate material. Now we're going to do a little bit of comparison. These bullseye craters have been, a number have been discovered on our moon. There are actually a few of them on Earth. This one in particular is in Russia, called Potomsky Crater. And of course we can recreate that relatively quickly on the lab. We can take a look at some other evidence we have for formation process. Devil's Tower in Wyoming, you can see the linear stacking of material, is just as we do in our other experiments here in the lab. This can also be looked at a little closer, and you can see this is salt, grains of salt that are stacking up just like they are on the Devil's Tower. So in my opinion, yes, electricity does have a major effect on surface formation, and there'll be a lot more to learn when we start looking for it, now that we know what to look for. So having said that, peace and love, big heads up.